Welcome back to Mechanical Engineering Made Simple. So I want you to picture this. You're sitting in a window seat on a commercial airliner, maybe 30,000 feet in the air, and you're descending toward a runway.
Always a tense moment for some people.
Right, exactly. And you hear that massive hydraulic whine right beneath the floorboards, and suddenly just tons of heavy metal, the landing gear drops down into this freezing, rushing airstream.
Moving at incredible speeds.
Yeah, and those metal struts and the wheels, they're swinging out, passing within fractions of an inch of the fuselage, like folding outward and locking into place. And it just happens perfectly every single time.
Every time.
Which, I mean, have you ever wondered what actually guarantees that those massive, heavy, fast-moving metal bars don't just, smash into each other and tear the wing apart?
Well, I mean, it feels like magic when you watch it out the window, but it's actually a highly specific, very rigorous language. It's essentially a language of pure geometry.
Just geometry.
Yeah, geometry. Before a single piece of steel is ever forged, or, before a single motor is turned on, that entire complicated ballet of the landing gear is mapped out using a field of study called kinematics.
Kinematics.
Right. It's the invisible architecture behind literally every moving thing in our modern world.
And so that is our mission today. We are taking a deep dive into the absolute bedrock of mechanical design. We're going to explore kinematics, which is, like you said, the pure geometry of motion.
Exactly.
We're going to unpack these terrifying-looking formulas that engineers use, break down exactly what those variables mean in the real world, and really explore how you can map out and graph these complex mechanical designs yourself.
Which is incredibly relevant for anyone trying to actually build something today. I mean, kinematics is the foundational step. You're basically stripping away the weight, the mass, all the pushing and pulling, and you're just looking at the theoretical paths, the angles, the curves.
It's because if you get that wrong.
If you get the geometry wrong, yeah, no amount of horsepower is going to save your machine from just completely destroying itself.
Wow, and we're tailoring this entire conversation directly to you, the listener. Because if you spend any time, browsing engineering forums or watching machining videos online, you see the exact same practical questions popping up over and over again.
Oh, constantly.
People are always asking, like, how do I design an over-centered device that actually locks? Or, how do I create enough clamping force to hold two pieces of metal securely against massive pressure?
Or how do you even measure that clamping
Yes.
force?
How do you measure it? How do you graph it out on paper? And what's the actual underlying mathematics that guarantees it won't just snap in half the second you let go of the handle?
We're definitely going to cover all of those practical applications today. We're taking that theoretical math that, looks so intimidating on a chalkboard, and we're connecting it directly to the physical hardware that you might literally have on your workbench right now.
That's awesome. Let's set a framework for this first, though. I kind of like to think of the math of kinematics as being a lot like a choreographer's sheet music for a massive ballet.
Okay, I like that.
Because if you aren't trained to read it, looking at that paper is just baffling. It's a bunch of abstract symbols, right? Numbers, intersecting lines. It seems totally detached from the physical reality of a stage.
Yeah, just gibberish to an outsider.
Exactly. But to the trained eye, that exact mathematical sheet music dictates precisely how incredibly heavy physical objects are going to, dance in the real world.
Right.
It mathematically guarantees that these metal links and gears and actuator arms can swing past each other at thousands of revolutions per minute without ever colliding or jamming or catastrophically failing.
That analogy actually holds up perfectly, especially when you realize that the consequences of a bad choreography in engineering usually involve, catastrophic structural failure.
Yeah, a lot worse than a dancer tripping.
Exactly. If the math is wrong, the machine dies. Sometimes literally explodes. But to truly appreciate the algebraic equations we use to graph out modern high-speed mechanisms today, we actually had to look backward first.
Right, because humanity didn't just start with calculus.
No, not at all. Early engineering was born out of just a desperate need to multiply human physical strength just to survive and build things. We only really developed the complex math when the physical machines became too complicated to just hold in our heads.
Which means we really need to start by looking at how humanity even began to categorize motion in the first place. You can't just wake up and invent a robotic assembly line. You need a vocabulary first.
You need language, yeah.
And looking back at the historical records, that vocabulary really starts to formalize around ancient Rome and Greece. There's this fascinating military engineer named Vitruvius who was writing around, I think, 28 BC.
Yeah, Vitruvius provides such a brilliant window into the ancient engineering mindset. When you read his texts, his definition of a machine is just stunningly pragmatic.
How did he define it?
He described it simply as a combination of timber fastened together, chiefly efficacious in moving great weights. That was it.
Just moving heavy stuff.
Right. There was no discussion of elegant, continuous, cyclical motion. There was no theory of velocity or acceleration. It was entirely about brute force.
Like, how do we lift this massive multi-ton stone block to the top of a temple?
Exactly. You take some timber, you fasten it together, and you overcome your physical human limitations.
It's pure utility. But then, if we fast forward about a century, we get to Hero of Alexandria. He's living in the absolute epicenter of ancient learning at the time, and he essentially writes the textbook on the engineering practice of his era.
Hero of Alexandria is a giant in this story.
He's the one who categorizes the 5 simple machines, right?
Yeah, he looked at the chaos of all these different wooden contraptions people were building and realized they all boiled down to just 5 fundamental building blocks. He defined them very specifically as tools for moving a given weight by a given force.
And those 5 were the lever, the windlass, the screw, the wedge, and the tackle block, which is basically what we'd call a pulley today.
Right, a pulley system. And it's amazing to think that for nearly 2,000 years, the greatest engineering minds on Earth believed that those 5 mechanical powers were the absolute atomic elements of physics.
Everything, no matter how complex, was just a combination of lever, a screw, a wedge, a windlass, or a pulley.
They were the alphabet of mechanical design. And, you can write some incredibly complex poetry with just a 5-letter alphabet. Ancient engineers weren't just lifting stones, they were building sophisticated continuous motion devices using just those blocks.
Yeah, and a perfect example of that is something that completely blew my mind when I first read about it. We're talking about a Roman odometer from roughly the same era as Vitruvius, so around 28 BC.
Attributed to a Greek inventor named Sitsibius.
Yeah, Stesibius. And when you hear Roman in 28 BC, you probably picture, like, chariots and gladiators, not a highly precise automated mileage tracking dashboard.
No, it sounds completely anachronistic.
It does. But the internal kinematics of this device are absolutely staggering.
Oh, the Sitsibius odometer is a masterclass in reducing rotational motion into a functional intermittent output. To picture this, just imagine a standard wooden carriage rolling down a stone Roman road.
Okay, got it.
The carriage has a wheel that is exactly 4 feet in diameter. The engineers attached a tiny gear with a single tooth directly to the axle of that 4-foot wheel.
Wait, just one tooth?
Just one tooth. So every time the carriage wheel makes a full revolution, that single tooth comes around and strikes the next component in the chain.
Okay, so what's the next component?
The next component is a massive horizontal gear with exactly 400 teeth. That single tooth gear on the axle meshes with the 400 tooth gear.
Oh, wow. So stop and think about the sheer reduction ratio happening there. The carriage wheel, rolling along the dirt, has to spin 400 complete times just to push that giant flat gear through one single, agonizingly slow revolution.
Exactly. And that ratio wasn't random at all. Based on the circumference of a 4-foot wheel, 400 revolutions translate to exactly 5,000 feet.
Which, in the ancient world, was
Precisely 1 Roman mile.
That is brilliant.
But the true genius of the device isn't just the gear reduction. It's how it actually signals the human operator.
This is the best part. Because, obviously, the designers didn't have digital screens, so they created an auditory dashboard.
Right.
Resting on top of that giant 400-tooth gear were small stones, or like pebbles, sitting in little carved-out holes. And as that giant gear finally completes its one slow 400-turn revolution, the hole containing a stone aligns perfectly with a metal tube that drops down into a bronze vessel below.
And the stone drops down the tube, strikes the bronze bowl, and makes a loud ringing clink.
So the operator sitting in the carriage just listens. Every time they hear that sound ringing out over the noise of the horses, they know they've traveled exactly 1 mile.
Yeah, they are translating continuous, messy, high-speed rotational motion at the wheel into a slow, precise, intermittent auditory output.
It's just a beautiful piece of machinery, but, it forces a massive question. When Stesibius or Archimedes were building these things, they didn't have the calculus of motion. They didn't have graphing calculators or algebraic input-output equations. So how did they actually do it?
That is the million-dollar question.
Were they just guessing? Like, did they just carve a massive wooden gear, slap it on a cart, drive a mile, realize they were 50 feet short, and then shave a bit of wood off through endless trial and error? Or did they just have this freakish, innate intuition for spatial geometry that modern engineers have lost because we rely on formulas?
It's actually a really profound debate among engineering historians, and the reality sits somewhere in the middle. These early builders absolutely possess a spatial intuition that would put most modern engineers to shame.
Because they were so hands-on?
Exactly. Their intuition was honed by decades of physical craftsmanship, actually feeling the wood and metal in their hands. But intuition only scales so far. We know from historical records that there was a massive, expensive, and often very dangerous amount of trial and error involved.
And I guess trial and error is fine when you're building a water wheel out of wood that turns at like 5 revolutions a minute. If it jams, the wood creaks, the water spills over, and you fix it.
Right, the stakes are relatively low.
Mm-hmm.
But trial and error becomes completely unacceptable when the Industrial Revolution hits. Suddenly, you aren't working with a wooden water wheel. You're working with steam-powered steel turning at 1,000 revolutions a minute.
Which changes everything.
Completely.
Mm.
If the spatial intuition of your designer is off by a fraction of an inch, the steel doesn't just creak. It binds, the pressure builds, and the machine violently explodes, taking the factory and the workers with it. That physical limit, the point where machines became too fast and too deadly for human intuition, that's what forced the invention of rigorous mathematical frameworks. We had to be able to predict failure on paper before we ever built the machine.
Which means that old vocabulary of the 5 simple machines was no longer enough. The guy who really modernized how we talk about machine parts was a German kinematician named Franz Reuleaux, writing much later, around 1875.
Reuleaux is basically the father of modern machine design vocabulary. He looked at the booming industrial landscape of complex textile mills and steam engines, and he realized Hero's 5 building blocks were basically obsolete.
So what did he replace them with?
He categorized them as the 6 modern mechanical components: the crank, the wheel, the cam, the screw, the ratchet, and what he called tension compression organs, which basically just means belts or chains.
Let's linger on that for a second, because just changing the names doesn't really sound like a revolution. Why was it such a big deal to categorize a crank as fundamentally different from a ratchet?
Because it allowed engineers to modularize motion. Think about a ratchet. A ratchet is a device that allows continuous motion in one direction, but instantly locks and prevents motion in the opposite direction.
Like a socket wrench.
Exactly. Whereas a crank simply translates circular motion into linear motion, or vice versa. By giving these distinct specialized names and defining their isolated geometric behaviors, Reuleaux gave engineers a library of predetermined motions.
Oh, I see.
You no longer had to invent a machine from scratch. You could just select a crank module to get a linear push, attach it to a ratchet module to get one-way indexing, and suddenly you're building complex automated factory equipment simply by snapping conceptual Lego bricks together.
Okay, so Reuleaux gives us the Lego bricks, but to actually turn this into a rigorous predictive science, we need the math. And this brings us to a massive paradigm shift in engineering history, pioneered by the mathematician Leonhard Euler and later expanded by the physicist André-Marie Ampère.
Yes, Ampère.
Ampère is actually the one who coined the term kinematic in 1834.
And that moment in 1834 is really the birth of the modern discipline. What Euler and Ampère did was realize that trying to design a machine by calculating everything at once was mathematically impossible for the human brain.
There are just too many variables.
Way too many. If you sit down and try to calculate the exact path a steel robotic arm needs to take, while simultaneously trying to calculate the weight of the steel, the friction of the joints, the gravity pulling it down, and the force of the motor pushing it, the equations become incredibly tangled. It is a total nightmare.
You just hit a wall.
So Euler proposed a radical idea. He said, let's separate the problem. He split mechanics into 2 distinct fields: kinetics, which we often call dynamics today, and kinematics.
Okay, what's the difference?
Kinetics deals with the brute reality of the physical world: the forces, the mass, the inertia, the friction, the heavy lifting. Kinematics, on the other hand, is a fantasy world. It's the pure geometry of motion. In kinematics, you deal only with distance, time, velocity, and acceleration. You literally pretend the metal weighs absolutely nothing. You pretend there's zero friction.
Wait, so you temporarily ignore reality so you can focus entirely on the choreography?
That is the genius of it. You just ask a simple geometric question. How long do these rigid lines need to be, and at what angles do they need to be pinned together, so that when I rotate line A by 10 degrees, point B moves in a perfect smooth arc to land exactly on top of point C.
Right.
Once you solve that geometric puzzle, the kinematics, and you have your perfect mathematical path, then you bring the kinetics back into the picture. You look at your path and say, okay, this path requires moving a 50-pound piece of steel in half a second. How big does the motor need to be to generate that force without the steel snapping?
Separating the geometry from the force made modern engineering possible.
Absolutely.
Which brings us to the actual math. We've set the stage, we know what kinematics exists, so let's look at the bedrock. If you want to understand how a mechanical system is going to behave in the real world, you inevitably run into the foundational equation of motion.
Here we go.
It looks like this. mx double dot plus cx dot plus kx equals f of t.
And for a lot of people, hearing a string of algebra like that immediately triggers math anxiety. But if you break it down, it's actually incredibly intuitive. It is essentially a mathematical tug-of-war describing a physical object trying to move.
Let's make this auditory and visceral. Let's walk through that equation term by term, starting with the very first chunk. mx double dot.
Okay, the M stands for mass. Just picture a heavy, solid block of steel. The x double dot, that is an x with two little dots over it, represents the second derivative of displacement with respect to time.
Okay, for those of us who haven't sat in a calculus class in a decade, what does a second derivative of displacement actually feel like in the real world?
Let's build up to it. Displacement, which is just the letter x, is where the block of steel is located. Say it's sitting at the 0 mark on a ruler. If you move it to the 5-inch mark, its displacement is 5 inches.
Simple enough.
Now, if you track how fast that displacement changes over time, you get velocity. That's the first derivative, written as x dot, so an x with one dot. It's moving at 5 inches per second. Now, if you track how fast the velocity is changing over time, say it goes from 5 inches per second to 20 inches per second, you get acceleration. That is the second derivative, the x double dot.
Oh, I see. So the first term, mx double dot, is simply mass multiplied by acceleration.
Okay.
It's Newton's second law, sitting right at the front of the equation. It represents the sheer force required to take a heavy piece of steel from a dead stop and force it to speed up.
Exactly. Now look at the second term, cx dot. We know x dot with one dot is velocity. The c stands for viscous damping. Imagine your block of steel is not moving through empty space, but it's completely submerged in a vat of thick oil, or it has a heavy-duty shock absorber attached to it.
Like, if you push your hand slowly through a pool of water, it's easy. But if you try to punch the water as fast as you can, the water violently pushes back against your hand. The resistance gets exponentially stronger the faster you move.
That is exactly what cx dot calculates. It's the resistance force created by the environment, and it is entirely dependent on how fast you are moving. The damping factor, c, multiplied by your current velocity, x dot.
Which leaves the third term in our system, kx. We said earlier that x with no dots is just pure displacement, just how far the object has been pushed from its starting point. So what is the k?
The k is spring stiffness. Imagine your block of steel is attached to a heavy coil spring. Or, more realistically in engineering, imagine the solid metal rod pushing the block actually flexes and bends a tiny bit under pressure, acting like a very stiff spring itself.
Okay.
The further you push the block away from its resting position, the greater the displacement x, the harder the spring tries to snap it back. A diving board is a great example. If you stand on the very edge and push down 1 inch, it pushes back a little. If you jump on it and push it down 2 feet, it violently throws you back up into the air. The force increases with displacement.
So if we pull back and look at the whole equation again, mx double dot, the force of the heavy mass accelerating plus cx dot, the sticky resistance of the oil dragging against its speed plus kx, the violent snapback of the spring resisting how far it's been pushed. All three of those internal forces combined must perfectly equal F of t.
Right, and F of t is simply the external force you or your motor are applying to the system over a period of time. This single equation is a perfect mathematical mirror of reality. It accounts for the heavy inertia, the sticky friction, and the bouncy flex of your entire physical machine.
That makes so much more sense now. In kinematics, though, we often strip away the mass, the friction, and the springs just to look at the motion variables, the displacement, velocity, and acceleration. And there's a massive trap here for engineers that the historical data highlights.
Oh, definitely.
When you're calculating acceleration across a complex trajectory, you're finding the change in velocity. You're basically taking one velocity vector and subtracting a previous velocity vector from it.
It sounds like simple subtraction, but it's actually incredibly treacherous, particularly when you're analyzing a machine moving at a relatively constant high speed. Because if an automated conveyor belt is moving smoothly, the velocity at point A is almost exactly the same as the velocity at point B.
Let's say velocity A is 100.01 inches per second, and velocity B is 100.02 inches per second.
Ugh. When you subtract two large numbers that are virtually identical, the result is an incredibly tiny number, in this case, 0.01. The problem is that in the real world, our measurements are never perfect. There's always a tiny margin of error in our sensors or our plotting.
Yeah.
When your final mathematical result is a microscopic number like 0.01, a tiny measurement error suddenly represents a massive percentage of your final answer. Engineering records show that in these specific scenarios where velocities are nearly equal, the percentage of error in calculating acceleration can skyrocket from a manageable 10% up to an astonishing 100%. Your math becomes completely untrustworthy.
Wow, 100% error. So how do you fix it? You can't just stop building high-speed machines.
You have to smooth the data out. Instead of sampling the velocity every single degree of rotation on your input crank, engineers will often calculate the average velocity vectors over a much larger sweep, say measuring every 15 degrees instead of every 2 degrees.
I see. It creates a larger delta between the two velocity numbers, which dilutes the measurement error and gives you a reliable acceleration curve.
Exactly.
Okay, so we know how to reliably measure basic velocity and acceleration. But real machines aren't just a single block moving in a straight line. They are webs of interconnected metal. And the most common building block is the planar four-bar linkage.
A classic.
Imagine four distinct metal bars pinned together at their ends to form a closed loop. If you bolt one of those bars rigidly to the floor and you grab another bar and start turning it in a circle, the other two free-floating bars are going to drag each other through incredibly complex, swooping figure-8 paths. How do we mathematically graph a chaotic, interconnected system like that?
Well, for centuries, the only way to do it was graphical. An engineer would literally take a giant sheet of tracing paper, a compass, and a ruler, and they would draw the physical linkages. They'd rotate the input, crank 5 degrees with a protractor, redraw the whole system, trace a dot, move it another 5 degrees, redraw it, and so on.
That sounds agonizingly slow.
It was. And you could never mathematically guarantee the final position, because a pencil line is always going to have some thickness and error.
So to mathematically guarantee the path, we have to move from drawing to algebra. And to do that, we use algebraic input-output equations, commonly called I/O equations. But there's a massive mathematical hurdle here. The joints of these metal bars are rotating in circles.
Right. And rotating joints are defined by angles, usually denoted by the Greek letter theta. Your motor turning the input crank is driving an angle, say theta 1. The output lever you're trying to control is moving at another angle, say theta 4.
And as soon as you have angles, you're dealing with trigonometry, sines and cosines. Why are sines and cosines such a nightmare for mechanical engineers trying to design a machine?
Because trigonometric functions are cyclical and infinite. A sine wave loops up and down forever. If you're trying to write an equation that tells a computer, I need the robotic arm to be at exactly this xy coordinate, a trigonometric equation might essentially say the arm will be there at 10 degrees and also at 370 degrees and also at 730 degrees into infinity.
That doesn't really help you build a physical machine.
Not at all. They are incredibly difficult to manipulate when you're trying to synthesize a single rigid real-world mechanism. You want standard algebra, where you plug in one number and get one definitive answer.
And this is where a brilliant mathematical trick comes into play, the tangent half-angle substitution. It's a translator that turns confusing infinite circles into straight, measurable algebraic lines.
The substitution works like this. You take your rotating input angle, theta 1, and you divide it by 2. Then you take the tangent of that new angle. You set that entire chunk of math equal to a simple algebraic variable, let's call it V1. So V1 equals tangent of theta 1 divided by 2. You do the exact same thing for the output angle, turning theta 4 into V4.
And by making that specific substitution, all the sines and cosines magically cancel out of your complex I/O equation.
Yep. You are left with a pure polynomial algebraic equation containing only V1 and V4. You've basically transformed a chaotic, rotating physical geometry into a continuous algebraic curve that you could easily plot on a standard coordinate graph.
When you look at the historical charts used to design things like an internal Geneva wheel, which is that classic clicking intermittent motion mechanism you find inside old analog watches or movie projectors, they used these exact I/O equations.
Right.
They plotted the angular displacement of the driven output gear on the y-axis against the continuous rotation of the driving crank on the x-axis.
And when you use these formulas to plot these continuous curves on a graph, something incredibly profound happens. You start to see mathematical anomalies that predict physical reality. The most famous of these is the double point.
Let's visualize this. You have your XY coordinate plane, and you're graphing the algebraic curve of your four-bar linkage. It swoops up, loops around, and crosses back over itself, creating an intersection. That point where the curve intersects its own path is a double point. Mathematically, it means that at that exact coordinate, the curve has two different tangent lines. But what does a self-intersecting loop on a piece of paper actually mean to a guy holding a wrench?
It is the exact moment the machine physically locks up or reaches its absolute limit.
Yeah.
Physically speaking, the double point corresponds to the extreme mechanical orientation, where two of the physical metal links in your four-bar system perfectly align in a dead straight line.
Like they stretch out as far as they can possibly go.
Exactly. And because they're fully extended and aligned, they cannot move any further in that direction. The mechanism has reached a boundary. By finding the double points in the mathematical graph, an engineer instantly knows the physical mobility limits of their design before they ever cut a piece of metal. It tells you immediately whether a specific bar in your linkage will be a crank, meaning it's free to rotate a full, unrestricted 360 degrees, or if it's going to act as a rocker, meaning it hits a double point, stops, and just swings back and forth like a pendulum. Or, worse, if it's a zero rocker, meaning the math dictates the mechanism will just lock up instantly and won't move at all.
The math is literally dictating the physical constraints of reality. And engineers rely on these exact I/O formulas and double points to solve incredibly vital life-or-death design challenges. A classic application is the Burmester problem, which was first fully outlined by the German kinematician Ludwig Burmester in 1888. It's formally known as motion generation or rigid body guidance.
The Burmester problem is fascinating because it's a massive step up in complexity. Up to now, we've really been talking about guiding a single point through space. Burmester asked a harder question. How do you guide an entire solid body like a large, awkwardly shaped chunk of metal through a very specific sequence of positions and angles in space?
Because you don't just care where the center of the metal is?
No, you care about its exact tilt and orientation at every single millisecond of its journey.
This goes right back to my anatomy of the commercial airliner landing gear. The landing gear is a massive, heavy, rigid body. When it retracts into the wing, it can't just swing blindly. It has to fold up, twist at a very specific angle to clear the hydraulic lines, tuck perfectly into a tight cavity in the wing, and then a door has to snap shut behind it.
Right, and if the orientation is off by even 3 degrees, the wheel smashes into the fuselage, the gear jams halfway out, and the plane cannot land safely. The engineers solving that landing gear design are essentially solving the Burmester problem.
Oh, interesting.
They're using the tangent half-angle substitutions to graph the algebraic I/O curves, ensuring that the physical lengths of the metal struts guarantee a perfectly continuous path with no double points or lockups where they aren't wanted.
You see the exact same math on modern factory floors, too, with pick-and-place assembly robots. Picture a high-speed conveyor belt covered in delicate electronic components. A mechanical arm has to dive down from above, grab a tiny computer chip at a 45-degree angle, lift it up in a smooth arc, flip it horizontally, and plunge it into a circuit board without shattering it.
Those robotic joints are driven by motors, but the structural lengths of the arms and the limits of their motion are dictated by the kinematic synthesis. The algebraic curves mathematically guarantee that the robotic arm won't smash the product into the belt.
So we've explored how kinematics allows us to mathematically generate a perfect path of motion. We can make the part stance, we can swing landing gear and robotic arms gracefully through the air. But what happens when we need the motion to stop?
That's a huge question.
Yeah, here is a practical engineering challenge that dominates forums. It's one thing to make a lever swing. It's an entirely different beast to make a mechanism clamp down on a piece of material and hold it rigidly against hundreds of pounds of external force. Moving things is kinematics, but holding things still against immense pressure requires weaponizing kinematics to create mechanical advantage.
This is a fantastic transition because it bridges the gap between pure geometry and brute kinetic force. If you're building a jig on a workbench or assembling an aerospace frame, you constantly need to lock in an over-center device or create a massive, reliable clamping force.
Let's get extremely specific and break down a device highlighted in the engineering literature, the fastener with actuator pin. This isn't something you buy in a plastic bin at a hardware store. It's a highly engineered, precision clamping mechanism used in aerospace and heavy industry. Let's describe its physical layout so we can visualize it.
It looks a bit like a complex syringe. It has a main cylindrical body that is perfectly smooth on the outside, with a slightly tapered, bullet-like end so it can easily slide into a pre-drilled hole in a metal plate. The head of this cylindrical body, the part that stays on your side of the plate, is threaded like a bolt, and it has a wide winged lock nut spun onto it.
But the magic is really inside the cylinder. The smooth body has vertical slots cut right through the metal. Hidden inside those slots are 2 or more steel toggle wings. And running straight down the hollow center of the whole device is a spring-loaded actuator pin.
If you want a more mundane analogy, think about a heavy-duty drywall anchor you use to hang a television on a hollow wall. You push it through a small hole, and once it's behind the drywall, it expands outward so it can't be pulled back through.
Right.
This fastener is basically the aerospace equivalent of that drywall anchor, but elevated to a level where the exact compressive clamping force is mathematically charted and guaranteed.
Let's walk through the mechanics of how a technician actually operates this thing. Say you have 2 thick steel plates you need to clamp together, and you've drilled a hole through both of them.
Step 1 is installation. The technician takes their thumb and physically depresses that central spring-loaded actuator pin at the top of the fastener. Pushing that pin down internally acts on the toggle wings, forcing them to retract completely inside the smooth cylindrical body. So the slots are now flush.
It's entirely smooth, so the technician just pushes the entire fastener deep into the hole, passing completely through both steel plates.
Right. Once the tapered end emerges out the back of the second plate, the technician releases their thumb from the actuator pin. The internal spring instantly pushes the pin back up. That internal movement forces those steel toggle wings to violently flare outward, extending past the diameter of the hole.
It opens up like an umbrella on the back side of the plates. So now the fastener is physically trapped. You can't pull it out. But crucially, it's not actually clamping yet. It's just sitting loosely in the hole. To generate the crushing holding force, the technician reaches for that winged lock nut sitting on the threaded head on their side of the plate.
As they start turning that lock nut clockwise, the nut threads down and presses hard against the front steel plate. But because the nut can't move forward into the solid plate, the twisting action starts pulling the threaded central body of the fastener backward. And as that body pulls backward, it drags those flared-out toggle wings violently against the back of the second steel plate.
Ah, you're sandwiching the 2 steel plates between the lock nut on the front and the toggle wings on the back. As you crank that nut with a wrench, you're exerting a massive compressive force on the metal.
But how do we guarantee that force? How does an engineer ensure that turning a nut actually generates enough clamping pressure to hold the wings of an airplane together? This is where we bring the math of kinematics back in, specifically the concept of mechanical advantage and linkages. To calculate this, engineers rely on a specific formula, the angular velocity ratio,
Which is written mathematically as theta 4 dot divided by theta 1 dot. We mentioned earlier that the dot over a variable means velocity, so theta dot is angular velocity.
Exactly. So this ratio is incredibly simple in concept. It's the output speed theta 4 dot divided by the input speed theta 1 dot. And here is the fundamental secret of all mechanical advantage. Force is the inverse of the velocity ratio.
The inverse.
Yeah. If you design a linkage like the threads on a screw or the levers in a toggle clamp, so that the input moves very fast and covers a lot of distance, but the output moves incredibly slowly and covers a tiny distance, you gain a massive multiplication of force at the output.
Like the principle of a car jack. You pump the handle of the jack up and down 2 feet, moving your arms incredibly fast and doing a lot of work. But the car only lifts 1 fraction of a millimeter. That extreme difference in velocity and distance is what translates the 50 pounds of force from your arm into the 3,000 pounds of force needed to lift a car.
Precisely. By carefully manipulating the physical lengths of the links or the pitch of the threads on that fastener, engineers are deliberately driving that theta 4 output velocity as close to zero as mathematically possible right as the clamp closes.
And charting this out is a matter of life and death in heavy industry. Engineers take those algebraic I/O curves we discussed, and they apply differential calculus to them. They're hunting for the extreme limits. They want to map exactly what happens to the internal forces right at the overcenter point.
If you've ever used a heavy-duty toggle clamp on a woodworking bench or a piece of heavy machinery, you know exactly what the overcenter point feels like in your hand. You push the lever down to close the clamp. The resistance builds and builds. Your hand is shaking. The metal is flexing. You're applying maximum force.
And then suddenly, it violently snaps past a threshold. The resistance instantly drops. The handle slams down to the table, and it just stays there, locked down tightly on its own. You don't need to hold it anymore.
That snap is the internal kinematics of the linkage physically moving past the point of maximum extension. It crosses the double point we graphed earlier, moving just slightly over the center line. Because it's over the center line, all the massive compressive force from the clamp material is now pushing the linkage down into its locked position, rather than trying to push it open.
The graph guarantees that this exact sequence happens safely. Because think about the physics. Right at that peak before the snap, the internal compressive forces are staggering. If the engineer made the metal links too long, the math shows the mechanism will bind before it ever reaches the overcenter point. You'll push the handle, it'll jam, and it will never lock.
Conversely, if the geometry is correct but the materials aren't specified properly, the massive compressive spike generated right at the overcenter point will literally shear the steel pins in half before it can snap shut.
Ouch.
Yeah. The kinematic graph guarantees that the mechanism smoothly passes that peak force threshold and rests securely in a locked state, utilizing its own geometry to hold the load.
So using an over-center toggle mechanism or a threaded actuator is a fantastic way to generate linear clamping force to hold two flat plates together. But mechanical engineering is full of spinning parts. What if you're dealing with rotational motion? What if you need to lock a spinning drive shaft in place with absolute precision, meaning zero slop, zero wiggle, and zero backlash?
That is an entirely different level of complexity. When you're dealing with precise optics, aerospace instruments, or high-end robotics, you cannot rely on just cranking down a nut to hold a shaft still. A nut can vibrate loose. You need internal automated escapements and locking mechanisms that rigidly jam the shaft the exact millisecond you stop driving it.
And the engineering archives have some incredible, almost devious designs for this. Let's start with a mechanism literally designed for the vacuum of space. It's called the foolproof locking pin, developed by T.E. Othman, E.P. Nelson, and L.J. Zmuda, originally under contract to NASA's Marshall Space Flight Center.
This NASA pin is a brilliant kinematic solution to a deeply terrifying, life-threatening problem. To understand the pin, you have to understand the environment. In space, you might have a massive multi-ton solar panel array that is under immense spring tension, waiting to deploy. It's held back by a single pin.
Right.
If a technician or a robotic arm pulls that pin while all that shear force is resting on it, the pin acts like a bullet, and the violent sudden release of the panel could destroy the satellite or kill an astronaut.
So you need a pin that physically refuses to be pulled out if it's dangerous to do so. How did Othman, Nelson, and Zmuda build a pin that is essentially self-aware of danger?
They used a brilliant arrangement of internal detemp balls and grooves. Let's look at the layout. We have the main body of the pin, which is a forward-pointing metal sleeve. At the rear, there's a spring-loaded sliding handle. Inside the hollow center of the sleeve is a sliding plunger, which is also constantly pushed backward by an internal spring.
Okay.
The key to the entire lock is a group of small, hard steel detemp balls housed in holes drilled through the side of the sleeve and a matching precise groove cut into the receptacle hole in the spacecraft.
It sounds a bit like the quick-release chuck on a socket wrench,
Yeah.
where a little steel ball holds the socket on, but obviously much more complex.
Similar principle, but much higher stakes. Here's how the foolproof mechanism works. To install the pin, the technician pushes the sliding handle at the back. This pushes the internal plunger forward. The plunger has a narrowed section that aligns with the detent balls, allowing the balls to retract inside the sleeve. The pin slides smoothly into the receptacle.
And when to let go?
When the technician lets go, the internal spring pushes the plunger back, forcing its wider section against the balls, pushing them outward into the groove in the receptacle.
So the pin is now locked. But here is the genius part about removing it. The internal geometry is cut so precisely that when a technician tries to pull the handle to retract the balls must be perfectly centered over the groove to drop inward. If there's a massive shear load on the pin, say, that multi-ton solar panel is resting its weight directly on the side of the pin is slightly wedged against the wall of the receptacle.
And that slight wedging misaligns the detemples of the groove by just a fraction of a millimeter. Because they are misaligned, the balls physically cannot drop inward. The plunger is blocked. The handle refuses to move. No matter how hard the technician pulls, the pin will not release.
Which raises a massive operational question. With the NASA pin, if the load has to be zero to remove it, how do engineers calculate and manage the shear forces resting on that pin in a zero gravity or high stress environment to safely release it?
That forces a broader systems engineering protocol. Because the pin enforces this safety rule, the engineering team has to design secondary tensioning systems around the pin. A technician has to use a separate hydraulic jack or a motorized winch to lift the heavy solar panel slightly, taking the shear weight completely off the pin.
Oh, I see.
The moment the weight is lifted, the tension drops to absolute zero. The pin perfectly centers itself in the hole, the detent balls align with the groove, the plunger snaps back, and the pin slides out effortlessly. The internal kinematics of the pin literally force the human operator to make the environment safe before the mechanical action can occur.
It is geometry enforcing safety protocols. That's incredible. Now let's pivot from static pins to rotating drive shafts. Let's say you have a shaft that needs to spin, but the moment the motor stops, you need the shaft to lock solidly so it can't backdrive. The research details a mechanism called the trip roller clutch.
A trip roller clutch is a gorgeous piece of machinery. It achieves a rigid lock not by sliding a pin into a hole, but by intentionally wedging and jamming solid steel rollers between two precise, hardened surfaces.
Imagine a standard doorstop. You take a rubber wedge and kick it under a door. If someone pushes the door from the other side, the friction drags the wedge deeper into the gap. The harder they push the door, the tighter the wedge jams until the door is completely immobilized. A trip roller clutch is essentially a circle of high-precision steel doorstops.
Precisely. Let's look at the layout. You have an outer stationary ring, called a reaction ring, bolted to the frame of the machine. Its inner surface is a perfect smooth circle. Inside that ring is the drive shaft you want to control. Attached to that shaft is a specialized disc. The outer edge of this disc is not a perfect circle. It is cut with specific, shallow cam surfaces, creating little ramps or tapering gaps between the disc and the outer reaction ring.
Sitting inside those tapering gaps are small cylindrical steel rollers, and the system uses two distinct sets of these rollers. One set is spring-loaded to jam in the clockwise direction, and the other set is spring-loaded to jam in the counterclockwise direction.
This creates an automatic bidirectional lock. If a heavy load on the shaft tries to rotate it clockwise, the rotation of the inner disc grabs the clockwise rollers and violently drags them up the little cam ramps, wedging them tightly into the narrowing gap against the outer reaction ring. It instantly jams solid.
And vice versa.
Right. If the load shifts and tries to backdrive counterclockwise, the other set of rollers instantly gets dragged up their ramps and jams. The shaft is completely trapped by its own rotational force.
But obviously the machine needs to turn eventually. The mechanism is called a trip roller clutch because to intentionally turn the shaft with a motor, you have to trip or unjam those rollers first. The motor doesn't connect directly to the shaft, it connects to a release cage that sits between the rollers.
That's the clever part.
Yeah. When the motor starts turning, it nudges the cage, and the cage fingers physically push the wedged rollers back down the ramps into the wider part of the gap. Once the rollers are clear, the shaft is free to spin. The second the motor stops pushing the cage, the springs instantly snap the rollers back up the ramps, jamming the shaft dead in its tracks.
And this wedging principle is taken to its absolute zenith in an application known as the zero backlash knob.
Backlash is a term that really haunts engineers. If you've ever used a cheap stereo and turned the volume knob and you feel that little bit of loose, sloppy wiggle before the dial actually starts to engage the electronics, that loose wiggle is backlash.
On a stereo, backlash is an annoyance. On a surgical robot or a targeting telescope, backlash is catastrophic. If an automated assembly robot has 2 millimeters of sloppy backlash in its shoulder gears, by the time that angular error extends out down the length of a 3-foot robotic arm, the hand might be off its target by ½ an inch. It'll completely miss the part it's trying to pick up, or worse, smash it.
So how do you build a manual adjustment knob that has literally zero slop? The design for the zero backlash knob is incredible. It looks like a standard dial on a control panel, but the operation is entirely dependent on internal kinematic sequencing.
When an operator wants to adjust the dial, they cannot just turn it. They have to push the knob inward, depressing it just 1/16 of an inch into the panel.
That's a tiny, almost imperceptible movement, but internally it changes everything.
That tiny 1/16 inch inward depression engages a bidirectional clutch release cage by a keyway. This cage has little metal fingers that extend down between a set of locking clutch rollers, exactly like the ones we just described in the trip roller clutch.
While the knob is sitting idle, those rollers are violently jammed up their cam ramps by heavy springs, locking the shaft to the stationary panel housing. It's a solid, rigid block of metal.
But when you push in and begin to twist the knob, the rotation of that release cage causes those metal fingers to physically cam the locking rollers backward, forcing them down the ramps against the pressure of their springs. It pushes them into the wider part of the gap, unjamming the system and freeing the shaft.
You can now smoothly dial the instrument to whatever precise setting you need. But the magic of zero backlash happens the millisecond you stop turning. When you find your setting, you release your grip on the knob. The internal spring instantly pushes the knob back out that 1/16th of an inch.
And that outward pop completely disengages the release cage. Without the cage fingers holding the rollers back, the heavy roller springs instantly fire the steel rollers back up the cam ramps, wedging them violently against the outer race. The shaft is immediately jammed and locked in both directions. Because it relies on wedging rollers into a tapering gap rather than dropping a pin into a pre-drilled hole, there's infinite resolution. It locks at the exact microscopic angle you left it, with absolutely zero mechanical slop.
To add to the brilliance of it, the engineering diagrams note a built-in safety feature. If the operator forces the dial and the internal shaft hits a hard mechanical stop, but the operator keeps twisting with excessive torque, the knob is designed to slip on its friction plates. It protects the incredibly delicate internal jamming rollers from shearing themselves apart under human brute force.
We see a similar philosophy of precise locking in what is known as a controlled output escapement. Escapements are famous in clockmaking for regulating the picking motion, but in heavy machine design, a controlled output escapement is used when you want a heavy output disk to index forward by exactly 1 notch, and then lock with absolute rigidity until you're ready to move it again.
In this layout, you have a drive lever that swings back and forth.
Oh.
When it swings forward, it pushes against a steel pin mounted on a large output disk, rotating the disk forward.
But underneath that disk is the control escapement, a heavy, pivoted locking arm. While the drive lever is actively pushing the pin and turning the disk, the escapement arm is cammed down, completely out of the way. There's a cleverly designed slot in the input linkage that allows the tip of the escapement arm to drop down and hide.
But it doesn't stay hidden. The geometry of the slot is perfectly timed to the stroke of the drive lever. The exact millisecond the drive lever finishes its forward stroke and begins to pull away from the pin, the rotation of the input linkage physically forces the escapement arm upward out of the slot. The hardened steel tip of the escapement violently jams upward into a precisely cut notch on the underside of the heavy output disc.
It acts like a deadbolt sliding into a door frame. The output disc is instantly locked. It cannot drift forward from inertia, and it cannot be pushed backward. It is completely immobilized until the drive lever cycles all the way back, resets, and begins its next forward stroke, which automatically cams the escapement back down into hiding.
Let's pull back and connect this hyper-specific mechanics talk to our larger picture. We started this deep dive talking about the pure mathematics of motion, the V1 and V4 algebraic parameters, the tangent half angles, the continuous cyclical curves on a graph. Why do engineers go through the immense pain of designing complex camming fingers, wedging rollers, and controlled escapements?
Because backlash and mechanical slop are the absolute enemies of mathematical precision. The math on your graphing paper assumes a perfect, rigid universe. If your mechanical hardware has even a millimeter of play in its joints, then its physical behavior is instantly deviating from the algebraic curve you calculated. The machine is no longer following the choreographer's sheet music.
It's improvising, and improvisation in heavy machinery leads to destruction.
Exactly. By utilizing continuous algebraic curves, like the cycloidal curves found in high-end planetary gears, such as hypocycloid, epicycloid, and paracycloid curves, and combining them with these absolute zero backlash locking mechanisms, modern engineers enforce reality. They ensure that the physical steel and titanium respond perfectly to the theoretical math, no matter how fast the system is moving or how much force is applied.
So let's tie this entire journey together. We started at the absolute beginning, looking at ancient engineers like Sisybius relying on brilliant intuition to drop pebbles into a bronze bowl. We saw how the deadly physical limits of the Industrial Revolution forced Euler and Ampère to separate the geometry of motion from the kinetic forces, birthing modern kinematics.
We walked through the basic equation of motion, exploring the internal tug-of-war between mass, damping friction, and spring stiffness. We saw how engineers escaped the infinite looping nightmare of trigonometry by using tangent half-angle substitutions to graph clean, continuous algebraic curves.
Those curves allowed us to spot double points. the mathematical prediction of a physical lockup, and solved the Burmester problem, giving us the power to swing massive aircraft landing gear through complex three-dimensional spaces.
And then we translated that pure motion into brute holding force, exploring how to use the inverse velocity ratio to create massive clamping pressure and over-center toggle wings, and finally dissecting the ingenious zero backlash mechanisms that lock those movements down permanently.
The next time you're adjusting a precise zero backlash dial on a microscope or a piece of high-end audio equipment, or even just locking down a heavy toggle clamp on your workbench to hold a piece of wood, I want you to look at the metal in your hands. You are physically interacting with the mathematical principles laid out by Burmester, Euler, and Reuleaux centuries ago. You are holding the physical, real-world manifestation of those algebraic I/O equations. It's just a profound way to look at the invisible architecture of the machines that surround us every single day.
It changes how you see the mechanical world entirely.
And as we wrap up, I want to leave you with a final thought to ponder, something that shows that this science is far from a finished book. Everything we discussed today, the planetary gears, the four-bar linkages, the over-center clamps, virtually all of it belongs to the category of planar mechanisms. They operate in two dimensions, essentially moving flat along an invisible piece of paper. But the engineering literature points out a massive looming frontier. There is a virtually unexplored domain known as three-dimensional linkages, or space mechanisms.
Oh yeah, that's a huge frontier.
They operate in full XYZ coordinate space simultaneously. To date, only a comparatively small handful of these 3D kinematics have ever been investigated, and very little has been done to even formally classify them. So think about this. If we have mapped two-dimensional planar mechanisms so thoroughly that we can mathematically guarantee zero backlash and perfect motion control in automated factories and spacecraft, what incredible, entirely unseen machinery could humanity build once we fully map and master the kinematics of multidimensional space mechanisms? When we stop moving on flat paper and start designing in pure, unrestricted 3D space, what entirely new dances will the heavy metal of the future be able to perform? That is something to keep an eye on. Thanks for listening.